Good morning, good afternoon, or good evening, everyone. Thank you for the opportunity to present our recent studies titled First Principles Studies on the Structure and Stability of Defect Complexes and Clusters in Nitrogen-Doped Joukowsky Silicon. My name is Hao Hu. In the semiconductor industry, silicon is one of the most important materials, and the control of the defects in silicon wafer is critical. Typically, there are two kinds of point defects in Joukowsky's silicon materials. Intrinsic point defects, including vacancies and interstitial. Secondly, the impurities such as oxygen, which induced from the silica crucible during the Joukowsky crystal growth, is considered unavoidable. When we're talking about defects, certainly we care about those large size defects, such as crystal originated particle, we call so-called COPs, which is composed of vacancy clusters called void. The COPs impact on the most devices, which cause the degrading of the GOI, the gates outside integrity, and also the box micro defects, so-called BMDs, which includes oxygen precipitates that serve as an intrinsic gathering center for harmful metal contaminations, and improves the mechanical strength of the wafers. The BMD also need to wafer deformation or overlay issues in a device manufacturing if excessive. The research objectives is to investigate the structural and energetic characteristics of defect complexes involving nitrogen, oxygen, and vacancy in Joukowsky silicons using DFT calculations, and to understand how nitrogen doping affects the defects in Joukowsky silicon. Defects in silicon can significantly impact the performance of electronic devices. Thus, controlling these defects is crucial for improving technology. In these studies, we will go through all the details about the isolated point defects, defect complexes, the defect clusters. The computational methods used in this study, such as the density functional theory, DFT calculations, as the main method to study the atomistic details of defects in silicon. For the electron wave functions, the Gaussian and the plane wave GPW approach is used on the basis of TZV2 heat, MOPOT, and CP2K code. This approach combines localized functions and plane wave to represent electronic states, streamlines the calculation process, imagines using both a zoomed in and wide angle perspective to understand the scene better. For exchange correlations interactions, the scan meta GH functional for the exchange correlations interaction was crucial in assuring quantitative accuracy. The functional goes beyond simple approximations by considering additional detail in second-order gradients of the electron behavior. Just thinking of it as using the highest resolution camera to capture more nuanced details of the landscape. Also, we use up to 17,028 lattice size supercell for defect cluster modeling. For bounding analysis, use the crystal orbital Hamilton population, or called COHP, and electron localization function, ELF. Also use the Vienna apps initiates simulation package, VASP, for wave function calculations. These are some so-called results in our study. So for the isolated point defects, such as frequency, which is based on the Jans-Tanners distortion, the symmetry, the 4 Darlington bonds, and the labeling under coordinates silicon atoms. Formation energies for 4 EVs, reconstruction bonds between the short silicon to silicon pair, origins of the deep acceptor level. And oxygens, the silicon bond center site, the symmetry of silicon bonds angle at 166 degree. The nitrogens on the split side, the doubling bonds on the labeling silicon atom. We also studied the defect complex based on the BON configuration, such as V2. So this is a number of doubling bonds reduced by 2, the energy reduced by 2.06. The oxygen is staggered structure. The silicon bonds angle 162 isolators oxygen and 131 to 136. This is based on the staggered structure. And the N2, the anti-parallel configurations, all atoms with variable coordination numbers. Also, the complex such as VO configurations. For example, VO is also called A center. The 2 doubling bonds terminated by oxygens, bound energies at 1.85 eV. So reconstructed bond between the 2 unders coordinate silicon atoms. Origins of a deep acceptor level. VO2 is on the D2-dit symmetry bound energy is at 1.62 eV. There's a complex of V2O, V2O2. For V2O, the bonding energies at 1.6 eV, V2O2 bonding energy at 1.75 eV, as shown in the page. So complex such as the NO complex, the NO or NO2 is a shallow thermal donors. The silicon, nitrogen, silicon, oxygen four-member rings as the core structures. The over coordinates are O as the origin of the electrical activities. The synchronize and the N2O or N2O2. So N2O's bonding energy is at 1.02 eV, N2O2 bonding energy 0.95. The MV complex, this is also one of the key studies in this research. The MV is on the more stable structure comparing with the TEAD configurations. The off-center substitutional nitrogen displays along 111's direction. The three identical silicon nitrogen bonds and the bonding bonds on the fourth silicon atom. The formation energy is 0.18 eV higher than that of the nitrogen. The N2V, the both nitrogen atoms on fixed site, both atoms having the favorable coordination numbers. The bonding energy is 2.09 eV. N2V2, the most stable, the NV complex. The bonding energy is 2.4 for N2 NV plus NV, or 4.13 eV on N2V plus additional vacancy. It's a treated symmetrics with two substitutional nitrogen atoms on the labeling site. This complex NVO complex, both NV and N2V2 can be combined with the additional interstitial oxygen atom. The oxygen atoms on silicon bond center site rather than on the silicon nitrogen bond center site. The vacancy provides the space for relaxation, as shown in the figure A and B. So there are also design on the defect cluster such as void. As shown, this is a typical void structure. It's diamond in a diamond lattice. The void favors octahedral shapes with 8-111 plane as the surfaces. Reductions in the number of bonding bonds as the driving force of these agglomerations during cooling process. Oxygen atoms on the vertex of voids can also terminate bonding bond. Substitutional nitrogen atoms can also terminate bonding bonds on the surface of the void more effectively than oxygen atoms, thereby stabilizing voids. By decreasing the surface energy of voids, increase the specific surface area of voids, decrease the size of COPs, and increase the concentration of COPs. Also, we studied the clusters such as oxygen precipitates. The two different kinds of oxygen precipitates. One of them is homogeneous nucleation of oxygen precipitates based on 1-1-1 chains. Ion orientation chains are energetically favorable. The silicon-oxygen 4-member rings in the middle of a long chain may contribute to electrical activities, as shown in the figures. Another kind of oxygen precipitate is based on the heterogeneous nucleation of oxygen precipitates. The three possible nucleation centers for oxygen precipitates, the Vs, Nvs, N2V2, all of which has a space for stress relief caused by the agglomerated interstitial oxygen atoms, as shown in the figure A, B, and C. So from the studies in this, we find out N2V2 can continuously capture oxygen atoms and is energetically stable. Nitrogen doping can enhance formation of oxygen precipitates by providing additional nucleation center N2V2. This is the findings in our study. The nitrogen can reduce the size of voids in silicon by forming stable complexes with frequencies. This means that nitrogen doping can help minimize the negative effect of defects. Nitrogen and oxygen can coexist on the surfaces of the voids, which may help reduce the surface energy of these voids, making them more stable. Nitrogen-doped silicon is expected to enhance the formation of oxygen precipitates, which can be beneficial for certain applications. Thank you. I'm welcome for your questions.